So thank you very much for the introduction. So it's a big pleasure for me to be here in Brazil. And so today I will speak about sphere packings and Fourier interpolation. So at this talk we will travel back and forth between discrete geometry and Fourier analysis. And so what we will see that each configuration of points in Euclidean space has its fingerprints on, in the space of d-dimensional functions, functions and d variables. On the other hand, if we are able to construct a function with, which attains certain extremal properties, this will give us some very useful information about optimal configurations in Euclidean space. And in particular, it can explain the crystallization in certain dimensions. So let's start with a classical geometric problem, which is a sphere packing. So it was already mentioned in a previous talk today, and so now let's give it a mathematical definition. So we consider a d-dimensional Euclidean space, and we will denote by b d of xr an open ball in of the center at x and radius r. And so we would say that we'll consider a subset, a discrete subset in d-dimensional space such that the distance between every 2 points is at least 2. Then we can consider, once we have such a set, we can consider a union of unit balls with centers at those points. And then those balls, they will not intersect, they might at most touch each other, and then we call such a union a sphere packing. And once we have a sphere packing, a natural question to ask is how dense is it? And so this question is not as easy as it seems to be, because of course we want to know, so the natural definition for a density is to say which portion of a volume is covered by our balls. However, you know that d-dimensional space, it has infinite volume, and it can also contain infinitely many unit balls. So we have to do a bit of analysis here. And so first we define a finite density like this. So we intersect our packing with some big ball with center at 0 and compute the density of our packing inside of this big ball. And this is a well-defined number. Then what we do, we can go to make this ball bigger, bigger, and bigger. And if we are lucky, this finite density will converge to some number, which we will call a density in this case. Even though it will not always be the case, we can think of some pathological situations when such a limit does not exist. And we can compute only the limit superior. And so now when we have defined density for one packing, we would like to find a configuration with a density which is as big as possible. And so we call, for each dimension, this number would be different, and we call this number the packing constant. And so this is the constant which we would like to compute for as many dimensions as we can, and say something for all of them. So what do we know about sphere packing constant? So here's what happens in small dimensions. So in dimension 1, packing problem is trivial, because almost like a ball in dimension 1 is just an interval, and all real line can be covered with unit intervals of length 2 with almost no space left. So in dimension 2, the problem is a bit more interesting. So here we can cover more than 90% of a plane with unit disks. And this is also the slide which is very similar to a slide you could have seen in the previous public lecture. So the bees know how to solve packing problem in dimension 2. And of course also mathematicians do know already for a long time, and it has a quite nice elementary geometric solution. And in dimension 3, here we have a jump of complexity. Packing problem in dimension 3 turned out to be much more difficult. So for 3 centuries it was open as a Kepler conjecture, and it was finally resolved by Thomas Hales. And so one reason to understand why is it so difficult in dimension 3. So in dimension 3 we have uncountably many different packings which are geometrically different and still have the same density. And so it was a very long and smart and tricky proof, which also required a lot of computer assistance. So what we know about other dimensions. So in this plot, so the blue line here shows what we know for about the sphere packings from dimensions from 1 to 36. And so blue line, it gives us the densities of the best known configurations. And the red line here, it is an upper bound. So in particular here I draw the upper bound, which was obtained by Kohn and Elkis, and I think it has not changed much since they published their paper. So what we can see from this picture, first is that the blue line and the red line, they both go down quite fast. So it means that whenever we go to high dimensions, possible density decreases. Actually, it decreases exponentially, because you see this plot, it's in a logarithmic scale. And so this we know. So we know that they both decay exponentially. Both actually, we know that it's for sure for red line. We know it for blue line, but at which rate it decays, we don't know. It's an open and very difficult question. Other feature which we can see from this plot is that this blue line is very irregular. So not dimensions, each dimension is like a different fairy tale. So some of, and on the other hand, for the red line we have here looks quite regular. So it means that with current proof techniques, we're unable to capture this somehow strange behavior of a blue curve. Another interesting feature is that at some point, actually, the red line and blue line, they seems like they meet. At least we can see it with a naked eye. And so, which we can see, they meet at point 1. What we cannot see on this plot, they do meet at point 2, and in 2 more points, 8 and 24. So now I will come to those 2 special dimensions. So in dimension 8, we have a very special, very nice configuration called the E8 lattice, which is somehow famous in all the mathematics. It has lots of nice properties, and so it can be given explicitly by its coordinates. So we just consider all the points in d-dimensional space such that all the 8 coordinates are either integers or all simultaneously half integers, and also the sum of all coordinates has to be 0 modular 2. And so the E8, it is the unique even unimodular lattice of rank 8. And so since it's an even lattice, it means that this squared distance between any 2 points is an even number. It means that minimal distance is square root of 2. So if you want to make a sphere packing of unit balls, we have to scale it. So multiply our lattice by square root of 2. Then we get a good set for centers of sphere packing. And so we know that actually this lattice is optimal. So this is the point where our red line meets the blue line. And we know that no packing of unit balls in Euclidean space has density greater than that of the E8 lattice packing. And it is this number, so it's about, the density is about 25%. And also we know that in some sense this packing is unique, so if we have another periodic configuration which attains the same density, it has to be isometric to the E8 lattice. Of course, we cannot rule out this for non-periodic configurations. For example, we can take E8, take away 1 ball. It means our configuration has kind of changed. However, its density is the same. And so the situation is quite similar in dimension 24. So in dimension 24, we have another remarkable lattice, which is called the Leech Lattice. So it's also even and unimodular. And so we know that there exist exactly 24 lattices like this up to isomorphism. However, only one of them has minimal distance between 2 points equal to 2. Because in all other cases, it's square root of 2. But this time, this minimal distance is somehow skipped. And this already gives us a hint that this lattice is a good candidate for a sphere packing. So this time we don't have to rescale anything because distance is already 2. So we can just consider union of all unit balls with centers at the points of Leech lattice. And then again we obtain the densest packing in dimension 24. So here's the theorem which we proved in collaboration with Henry Kohn, Abhinav Kumar, Stephen J. Miller, and Danilo Radchenko. It's that no packing of unit balls in a 24-dimensional Euclidean space has density greater than the density of a Leech lattice packing. And this number is this tiny number, which is about like 2,000, slightly smaller. It seems small, but actually for dimension 24, it's a very good result, as you might remember from our first plot with a red line and a blue line. For example, this number, it is bigger than the best node density we know for dimension 23. Or at least the best what we know at the moment. Of course, for dimension 23, we don't have any kind of a proof because it's one of those difficult dimensions. And so now let me tell you a little bit about the methods of a proof. So where the Fourier analysis comes from. So here is a theorem which was proven by Kohn and Elkis. And it says that if we fix some positive number R0, and for this number R0 we are able to construct a Schwarz function on d-dimensional space. And this function f, it satisfies the following 3 conditions. So first condition is that the function is non-positive outside of a ball of radius R0. Second condition is that the Fourier transform of f is non-negative. And the third condition is that our function is normalized in such a way that its value at 0 is equal to the value of its Fourier transform at 0 equals 1. Then we know that every packing in d-dimensional Euclidean space has density smaller or equal than the volume of a ball of radius R0 divided by 2. And so every mathematical talk is supposed to contain at least one proof. So I will show you a proof of this statement. So suppose that X is a subset of d-dimensional Euclidean space. And so here we scale it. We don't require the distance to be 2, but we require it to be R0. And also another assumption which we make, we assume that our configuration is periodic. So now we can write the following estimates. So remember we assume that we have a function f, it satisfies the conditions 1, 2, 3. And so we write, so if we want to estimate the density of this packing, so actually what we have to find out, we have to estimate the number of points of X modulo this periodic lattice L and compare it to the co-volume of the lattice L. So at this first step, what we do, we remember that our function was non-negative everywhere outside of the ball of radius R0, and because distance between 2 points is at least R0, we can write such an inequality. And the second step, we just rewrite the same inequality, but in a way which is more symmetric with respect to X and Y. So next, what we do, we use the Poisson summation formula. And rewrite our number in this form. Now we use a small trick. What we do, we will replace this double sum by a single sum. However, then we will take an absolute value squared of certain sum of exponentials. But after we've done this trick, now we see that all these numbers, which are multiplied by the values of f, they all have to be non-negative. On the other hand, we also know that the values of Fourier transform from the first, second condition, we know that they're also non-negative, and the value of f at 0 is equal to 1. So we just use this estimate and arrive at the following inequality. So now when we compare what we had here and what we have here, so now we can estimate the number of points of X modulo L by the co-volume of L, and then multiply it by a volume of a ball of radius R0 divided by 2, then we get exactly the statement of the theorem. So what we have seen in this proof is that this proof is quite wasteful. So here we threw away quite a lot of information about function f at this step, and also abandoned a lot of values of f at this step. So we have very kind of little hope that we will get a sharp bound. However, we will get some bounds, and this is what Henry Kohn and Noam Elkis have done in their paper in 2003. They used this method for all the dimensions from 1 to 36. They obtained some estimates, and as you've seen on a plot, in most of the dimensions there was quite a big gap between the blue line and the red line. And however, with two exceptions. So in dimension 8 and in dimension 24, and so actually also in dimension 1 and 2, but this case has already been settled, so it's not so interesting for us now. So we have these estimates. So what they proved that even if there exists some packing in dimension 8 which is better than E8 lattice, it can only be better by this number which is very, very close to 1. And similar result they obtained in dimension 24. And so this is these numbers, the numbers which they have been computed in 2003. But since then they have been improved a lot by Henry Kohn and his collaborators. So in the last papers they could replace this 0016 actually by 10 to the minus 60. And the same here. So you can think of it, it's actually somehow numeric, it's not 10016, it's a numerical one here and numerical one here. So what we would like to do now, we would like to replace this numerical one by a mathematical. And for this we still use the method developed by Kohn and Elkis. However, what we will do, so what was done in this paper in 2003, they were searching for some auxiliary functions f, but they did it in a numerical way. But so now we would like to find an explicit function which would satisfy the same conditions. So what one theorem I would like to present today is that there exists a Schwarz function of 8 variables which satisfies all these 3 conditions, which are the conditions of the Kohn-Elkis theorem, and here the value of R0 is square root of 2, which is the optimal choice in dimension 8. And also a similar result was obtained for dimension 24 in collaboration with Kohn, Kumar, Miller, and Redchenko. So what we proved together that there exists a radial Schwarz function of 24 variables, which satisfies all these conditions. And here the optimal choice of R0 would be 2, because this is the minimal distance between points in a Leech lattice. And so here is the plot of this function. So now between ourselves we call this function f a magic function, because it magically proves for us such a difficult geometric result. And so here, remember from the definition, this has to be a Schwarz function. So the function f and its Fourier transform, they decay very fast. So if I plotted you the function f itself, you would maybe see only this first bump and then nothing else. So I multiplied it by this auxiliary exponential. So one thing, of course, we can see from this plot is that the function is radial, and therefore we can represent it as a function of one variable. Because if we found one function, because all the 3 conditions of Kohn and Elkis, they are equivalent with respect to rotation. So if we have one function, we can average it over all the rotations and then obtain a radial function. And then this radial function, we can easily draw it and represent it here, which would be very difficult for function of 8 variables. Another thing which we can see here is that our function has many double zeros. And so where do these double zeros come from? Because you remember in the proof of the theorem of Kohn and Elkis, we had to abandon all those many values of function f. And of course our bound can be sharp if and only if all those abandoned values, they had to be 0. And so that's why we see them on this plot. All those double zeros. So here, let's just summarize what I said. The first, the function is radial. Second is that function has a lot of double zeros. And all those zeros, they are located at the numbers square root of an even integer. And the third remark, which I think seems like comes a bit from out of blue, is that so if we want to construct our function explicitly, we need to make some assumptions in which form are we going to search for this function. And so we made the following ansatz. So we want to look for our function in the following way. So we want to have for this multiple sign square, which will be responsible for all our double zeros. However, we need also some correction part. And we will search for it in the following form. It would be a Laplace transform of some function, which can be somehow, if we think of it as not a function of a real line, but a function of an imaginary axis, it can be extended as a holomorphic function to the upper half plane. And once we do so, so what I will show you today, that this function phi, even though the function f E8 itself seemed quite mysterious, even though we were able to compute it numerically, some very good approximations. However, this function phi, it will have a hidden symmetry. And this is a symmetry of the modular group. So the modular group gamma 1, it is a group of all 2 by 2 matrices with integer coefficients and determinant 1. And this function, it acts on the upper half plane by linear fractional transformations, like this. So here, this blue domain is a fundamental domain of this action. And so here I also draw all the translates of this line and of this semicircle under the group. So you can imagine what this action looks like geometrically. And so later in the talk I will explain how this symmetry arises and why is it natural to look for a symmetry like this. And so the idea behind our construction of the functions f E8 and f lambda 24, it was the hypothesis which we could first confirm numerically, is that a radial Schwarz function p, it is actually can be uniquely reconstructed from the following values. So if we have know the values of f at all square roots of integers, also the values of its derivative, and the same information for its Fourier transform, then we can reconstruct this function uniquely. And so I will show you more details on this formula later. So, and proving this statement rigorously, it's a still ongoing project together with Henry, Abhinav, Steven, and Danilo. And so it turns out that proving this interpolation for second order interpolation is a bit technical and difficult. However, we found together with Danilo that a similar phenomena happens also for simple interpolation. So now if you know not the values of function and its derivative, but what if you know only the values? So now the price would be that we require, so to say, twice more points. So we want to compute our function and its Fourier transform not at the square roots of even numbers, but just at the square roots of all integers. So this is the following theorem we proved in the easiest case for, well, just somehow, it would be natural to start from dimension 1, and in principle the same formula holds for radial functions in any dimensions. So we found that any Schwarz function on a real line satisfies the following identity, and the right hand side here it will converge absolutely. And so these functions which I have here, this C0, A, and they can be computed explicitly. And as interpolation functions, so they have a property that, for example, an, it vanishes at all square roots of integers except for its value at n. So here's the plot of these interpolation functions and their Fourier transforms. So here it turned out that it would be easier for us to work not with all real line, but to separate even functions from odd functions. And so another way to think about this result, it's not only as an interpolation formula, but also as a construction of some special kind of a crystalline measure. So what's a crystalline measure? So a crystalline measure, it's a temperate distribution such that this measure itself and its Fourier transform, they both have a locally finite support. So it, for example, so it means that we have some discrete set x and y, and so mu and y, there are some linear combination of delta functions located at those points. So we call that x is a support and y is a spectrum of this measure. And so if we make a definition, we want to know that we are defining not just an empty set. So here's one very simple example of such a crystalline measure, very natural one. So it's a Dirac comb. So it's just the sum of delta functions which are located at the integers. And one question is, do we have other examples of crystalline measures? So here I will show you one negative result. So if we ask some additional properties from our crystalline measure, then we can rule out everything except for those Dirac combs. So it's a quite recent theorem of Lev and Dalevsky, who say that if mu is a crystalline measure, and here we require that both support and spectrum, they are uniformly discrete. It means the distance between 2 points in x and in y, it has to be bounded from below. And if this is true, then mu can be also only a generalized Dirac comb. So it can be either Dirac comb, or its translate, or it's a Fourier transform of its translate, or some linear combination. And nothing else, only like finite combinations like this, actually for some commeasurable lattices. On the other hand, if we waive this requirement for x and y being uniformly discrete, actually we see that almost anything can happen. So here's our example. So the interpolation formula, it implies that we have the following continuous family of exotic crystalline measures, and exotic means that they are not generalized Dirac combs. And so here x, it's our free parameter in this family, and so we have one delta function located at this point x, and some other linear combination of delta functions which are located at square roots of integers, and with coefficients which are given by our interpolating by functions in our interpolating basis. So here we see that somehow if our points have to be distributed far away from each other, then almost like nothing is interesting is possible. If we allow points to come close together, as for example to a square root of n, then almost anything is possible. And of course, very interesting question is, so what happens in between? What if these locations, what if they grow like logarithm or some other power of n? So, and I think it's a totally open question right now. And so here a few words about the proof. So first, as I already told you, it's nice to consider separately odd and even components of Schwarz functions. And another trick which we do here, so if we have, my advisor always told me, if you have some sequence of objects which you cannot understand, or especially if those objects are functions, it's always good to consider generating series. So always consider generating series. So this is what we have done here. So here Bn and are our basis functions, and we believe that do exist, and they provide us this interpolation formula. And so now if we write two generating functions like this, then we will know that these generating functions, they satisfy a functional equation. And so how do we derive a functional equation? We take the interpolation formula we believe that is true, and we apply it to a complex Gaussian. And then this is actually the formula which we get. So we know that these functions g and g hat further satisfy this inequality, and also what we implicitly know about it, we know that this both g and g tilde, they are both one periodic in tau variable. So now what we can do, we can actually solve this functional equation explicitly. And we can do it using the methods which are already developed in theory of modular forms. In particular, we can use Eichler cohomology and the theory of modular integrals. And so this is how we obtain these integral representations which I've shown you in one of the previous slides. So from here it would be very natural to search for our function as an integral in of some modular object by a contour in the upper half plane. And so now let me briefly tell you about some work in progress. So here are two projects, and both are not finalized yet, even though I think that I really would like to speak about them. So the first is an application of our interpolation formula to partial differential equation, namely to the Gurza problem. And it's a joint work with Andrew Bakan, Hakan Hedemalm, Alfonso Montes Rodriguez, and Danilo Radchenko. And the second project is about universal optimality of E8 Lattice and Leech Lattice. And it's a joint work with Henry Kohn, Abhinav Kumar, Stephen Miller, and Danilo Radchenko. So let me start with an interpolation formula. So maybe I'll go quickly over it. So the Gurza problem, it's a problem of solving, so it's a boundary problem for such a differential equation, which is a hyperbolic differential equation. Sometimes it's called a canonical telegraphist equation or telegraphic equation. And so the question is, so we have such a differential equation, and we know that a restriction of its solution to x equals 0 is given by one function phi, and its restriction on another x equals 0 and y arises is this another function psi, and suppose that there is some agreement between them. So the question is, when can we find the solution? And so the first simple answer is to this question is quite classical. So we know that solution exists and it is unique, and it has a nice integral representation. However, next step of complication, what we can do, we can also put some growth conditions. So we want our function to be a solution of this problem, but we also don't want it to grow too much and x and y go to infinity. And in this case, it turns out that the problem already becomes overdetermined, and we get some non-trivial relations between the functions phi and psi. And so there was another interesting result recently obtained by Hakan Hedemalm and Alfonso Montes Rodriguez, is that suppose that we assume that our function y is reasonably nice, and if it's reasonably nice, then it can be written in such a way where a is some L1 function. And then what we want our function to now not suppose that we know our function not at this coordinate cross, but rather in a lattice on the coordinate cross. This lattice, which is pi times an integer. So what they show that if a solution vanishes at all these points, this means that it has to vanish in the whole plane. And what they also shown that there is actually a possibility for interpolation from this lattice points. And with our result on Fourier interpolation, we can write an explicit formula. So here are some technical conditions I'll probably skip. So this is the problem we are currently working on. And it says that there is we have a continuous sequence of solutions of this canonical telegraph equation, which are first they are bounded at this quarter plane, and they satisfy the following conditions. So each of the functions Rn, it vanishes at all by one of our lattice points on a cross. And moreover, if our function, if our y is a solution of a telegraphic equation, and it satisfies some boundness conditions, then actually it can be somehow uniquely interpolated from its values at those points, and the functions are and they are used as interpolants. And so now this was a short return into differential equations. So now we come back to discrete geometry. So of course, one way to, if you have a configuration of points in Euclidean space, one way to say whether points are optimal or not is to consider sphere packing. However, from physics and from other applications, we also have another very interesting family of optimization problems, namely energy optimization. So what we do, so we choose some potential function. It actually can be anything. It could be some nice, like a Coulomb potential, or for example, if we speak about sphere packing, you can also think like it's a degenerate problem, or when our potential is somehow infinite inside of for around 0, and then drops to 0 when it's far away from 0. And so when we give up the potential, first for every finite subset of Euclidean space, we can define the finite energy of this set in the following way. However, most interesting configurations in Euclidean space, they are actually infinite. So we next thing to analyze them, so if we want different configurations to compete between each other, we would like to fix their density, because we want our competition to be fair. It's like for boxers, we have to fix the weight. And so suppose that C is now some discrete, maybe infinite subset, then we can define the density of this set in the following way. And as we've seen before, of course, this density limit might not be defined at all. However, if our discrete set is regular, for example, if it's periodic, then the density is well defined, so we are fine here. And so now for such a nice set which has some density, we can compute its P energy in the following way. So in this case, we consider, instead of limit supremum, we take a limit infimum of the following sum. And if this limit exists, then we say that our configuration has a P energy, and it's equal to this number. So now the game we would like to play, we consider different configurations with the same density and try to find a configuration which has this density as small as possible. And in some cases, this minimal energy will be actually attained by some configuration. And in this case, we will say that C is a ground state for P. And so this actually the ground state, it can depend a lot of course it will depend a lot on our potential which we choose. And for some potentials and for some dimensions, situation actually can be very complicated. So one example here is like Gaussian energy in Gaussian potential in dimension 3. It's a very complex problem where I think actually for almost only for a few parameters we know what the best solutions should be, and there is a conjecture that the best solution is not even periodic. However, it could be that in some dimensions or for some nice family of energies, it could happen that one configuration is actually good for several potentials. And so we say that configuration C is universally optimal if it minimizes P energy for all completely monotonic functions P. So P should be a completely monotonic functions over squared distance. And completely monotonic, it means that somehow first it's decaying, it's concave, and all the other derivatives of P also have the right size. And again, if we give a definition, we want to know, is there at least one object which fits our definition? And so Henry Kohn and Abhinav-Kumar, they conjectured that, for example, these three lattices, they are universally optimal. So they conjectured that this is true for the lattice of integers, for the hexagonal lattice, A2, for the E8 lattice, and for the Leech lattice. And so Henry and Abhinav by themselves, they proved this statement for the lattice of integers. So we know that the lattice of integers, it is actually universally optimal. And now the work in progress, which I think we'll finish soon, is that the E8 lattice and the Leech lattice, they are also universally optimal in their dimension. And so I would like also to point out that the hexagonal lattice, it seems to be halfway between integers and E8, and for it we still don't have a proof, and here situation seems to be much more complicated, for example, than for E8. So now let me tell you, in the remaining 5 minutes, let me tell you about the idea of the proof. So here again we use the linear programming method, similar to the one we have used for packing problem. Here again our proof relies on a construction of a special function. So in this case we fix a potential P, and we would like to construct a Schwarz function f, which satisfies these properties. So first, that f does not exceed our potential P, and its Fourier transform is non-negative. Then if we have constructed such a function, then we know that the P energy of any configuration of density rho has to be at least rho times the Fourier transform of f at 0 minus the value of f at 0. And so now how can we construct such a function? So here what will be useful for us is the second order interpolation formula I've already mentioned once. So here is a more precise formulation of this principle that a Schwarz function can be reconstructed from its values and the values of its Fourier transform at the square roots of even integers. So what we now proved but have not published yet is there exists a collection of radial Schwarz functions with this property. So for any radial function f, such an identity will be true, and the right-hand side here will converge absolutely. Moreover, what is also true, if we now fix some possible values of f, so of course if it's a Schwarz function, so it means that the sequence of values it has to decay faster than any inverse power. Then we can also construct, just from this formula, construct some function f, and what we prove that this function also will be a Schwarz function. So it is somehow isomorphism between two linear spaces of Schwarz functions and fast decaying sequences. So now when we have this theorem, it will help us to construct our magic functions. So now again we fix some potential P, which will be a strictly monotonic potential. And so what we know that the only possible magic function f for it, of course because we want our bounds to be sharp. As in so here the proof that by similar considerations as we had all the double zeros for our magic function for a sphere packing case, here also what we require is that our magic function, it has to coincide with our potential function at all square roots of integers. Square roots of even integers. So the only possible choice for f would be this function. And so now it already will depend, of course, on our function p, whether the function f will also satisfy the necessary inequalities. So if in order for E8, now if we want to check that E8 minimizes such a p energy, it will be sufficient for us to show that f satisfies the following two inequalities. First, that it does not exceed our function p. So here now that it somehow interpolates our p up to second degree, but this inequality is still not given. There still might be somewhere like sporadic sign change. So we have to actually check it by some means which we have. And the same thing we also have to prove for its Fourier transform. So from the formula, of course, we know that the Fourier transform will have double zeros at all such points. However, we cannot rule out sign change anyways. And so another useful thing, so now if we want to prove universal optimality, we have to do this for all strictly monotonic potential functions. But here we are lucky because every strictly monotonic potential function, it's a linear combination of Gaussians. And so a configuration is a ground, if some configuration is a ground state for every Gaussian, then it will be also a ground state for all completely monotonic functions. And so it remains in 1 minute, what we have to do now, we have to just construct this function an, right? And here we do it by the same trick. Again, we consider generating functions, and we apply our prospective interpolation formula to a Gaussian, and we see that our generating function has to satisfy the functional equation. It's very similar to the functional equation we had before. And the only difference is that the generating function we had before, it was periodic. And function f, it's not periodic. However, it's very close to being periodic. It's like linearly periodic. So it satisfies this identity. So now we need to find a function which satisfies these three conditions. And so we can do so, again, by using a technique in the theory of optomorphic forms, and it's at least what we found. We did not find a theory which exactly fits this a bit more complicated situation, so we also had to invent our new technique. However, we were able to do so, and so the next step to see that the interpolation formula is true, now it will be actually equivalent, the existence of interpolation formula will be equivalent to the existence of such a function f, which satisfies this condition and also satisfies it has a moderate growth. And then the moderate growth, it will actually give us the convergence of our interpolation formula. And the last thing we have to do, we have to prove inequalities for this function f. So then the function f with parameter it, it will be the magic function for a Gauss exponential, for a Gauss potential with parameter it. So with parameter t, where t is a positive number. So if we have to check these inequalities, and checking these inequalities, the only way we found to do it is just by finding an explicit formula for f and then proving it numerically. However, now seems like our code is quite stable, so we were able to do so. So thank you very much for your attention.
Thank you very much for a delightful talk. I do not know whether we are meant to have questions, but I think it would be a very good thing if we had questions.
So in the two-dimensional case, do you think, the sphere packing is already solved, but do you think the linear programming bound can be solved as well?
Yes, so somehow we have very strong numerical indication that it can be done. And somehow, yeah, so I really hope that it can be done, and by not exactly, it doesn't work exactly the same way as it worked for dimension 8 and 24. So here still remains a lot of room for creativity, but I think maybe this is the problem which is like both interesting and also, from my feeling, it is doable.
Thank you. Other questions, please? No? Are there no other questions? May I ask a foolish question?
Yes.
What about non-lattice packings?
Do you mean, okay, so like the bounds which you obtain, they also apply to non-lattice packings. On the other hand, if a non-lattice packing is optimal, then as I think it's probably, its optimality could not be proven by this method, because this method, it works nicely when, so to say, the possible distances between points, they belong to some discrete set.
Yes.
And it's very difficult, I think, I cannot say that it cannot be true for a non-lattice packing, but it's very difficult to imagine a non-lattice packing with this property.
Right,
so
but how would the method of Combinatorics work for a non-lattice packing? Because there you are taking the dual lattice.
Okay, so the assumption I made there is that it's not a lattice. It works for periodic. So periodic is not the same as lattice, right?
All right.
And then, of course, like the one method we could use, that actually every packing which is somehow reasonably regular, it could be approximated by periodic packings. And of course, it's not as simple as I say. There is a bit of analysis here, but it's actually I think it's a theorem that for example, for packing problem, that the packing constant over all periodic packings is the same as packing constant over just all possible configurations.
Well, I said it was a foolish question.
No.
All right, no more questions, foolish or otherwise? Well, let us thank.
Just curious, do you think your methods and the methods that you presented give any insight to how the asymptotics of packings work? Or is it a completely different game there? But asymptotics indeed.
Yeah, I think somehow it can help some from above, from this like red line, but actually I think we don't know here because asymptotics in big dimensions, right? Yes, so I mean there is a couple of asymptotic Kapatansky-Levenshtein bound, and it is obtained by linear programming methods, and it's the best we have at the moment. At some points I tried to improve it, I could not do it, so it could be that actually Kapatansky-Levenshtein is the best we can do with linear programming. So I don't know it, but yeah, beating it is very difficult. However, what I think nobody knows at the moment are the actual bounds. Are they better than linear programming bounds? And it's an open question. So, for example, Sylvester Torquato, he has this like, meta conjecture that linear bounds are supposed to be the right ones, or linear bounds with certain restrictions are supposed to be the right ones. But he's not a mathematician, he's actually a chemist. So he has even a paper about this, but of course it's not a mathematical proof, so he has some reasons to believe that. So he even writes like a very, very precise asymptotic bound with many decimals in exponential, but yeah, actually I don't know. So now like from below, from what we can construct, it is like something like 2 to the minus d, from above like another, some constant to the minus d, and yeah. So it's still open.
The symmetry you have is reminiscent of modular forms. Is there an explicit connection?
Yes, of course. I just did not have time here. So when I solve these functional equations, I just have to write down some very explicit modular forms. And yeah, so in a papers, or maybe when I give other talks, sometimes I explain actually how it's constructed, how those modular forms are, what are they, and write them explicitly. Just I omitted that today because it seemed to be too much.
Very well. I think we can have at most one more question. No? Going, gone? Very well. So let us thank Maryna again.